what we're going to be looking at today, okay, is really, really cool because what we have in maths is kind of two different kinds of maths. And I don't know, could you raise your hand for me if anyone has heard these words, these adjectives applied to maths before? Anyone? Anyone at all? Pure and applied maths, yeah? Keep your hand up if you know at all what any of that means, yeah? Do you want to have a go? How would you summarize it for us?
So pure maths is stuff like theories and concepts, whereas applied is specific things like length and distance. Good,
yeah, fantastic. Okay, so I think that's a great, succinct illustration of it. Let me try and give you an example of these. Pure maths. Pure maths, okay. This is pure maths. Ready? Hold on. What should I do next? I'll put that there. There we go. It's a type. Okay. So have a look at that, right? Is that interesting? Guess what? It's been mathematically proven that noughts and crosses is an unwinnable game. If you know what you're doing, of course. It can be mathematically proven. It's not just like, oh, I played 100 games, and once we've played 100 games together, you've worked out how to do it, right? You really literally can't win. It should be a tie every time. That's been proven mathematically. What does that have to do with anything? Not much. It's pure maths. Okay, it's maths for its own interest. It's just like, oh, someone thought that was kind of curious and weird. Applied maths is kind of like the opposite. It's maths in the nitty-gritty of the real world. Like, I've got a problem, and it involves numbers, and I need to solve it somehow. Let me bring some maths to bear in order to do that. So what we're going to be doing today is really at the heart of what it means to have applied maths, right? We give you guys problems like, say, what have you been looking at recently? So financial maths, okay? That's applied math, it's real problems. But even so, it's problems that we've given to you. It's like, oh, okay, David has a part-time job working at, Macca's, and he earns such and such, and how much tax he pays, blah, blah, blah. That's a problem that we have contrived to give to you. Today, you guys will be crafting the problems, okay? So, very quickly, I want to show you something which I'm sure you have a look at quite a bit in recent times. So, you've been probably staring at this map quite a bit, thinking about, okay, this is the scenario that we are in. This is the kind of environment in which we are trying to solve a problem. Okay? Now, we are trying to head towards particular different solutions. So today I'm going to try and give you some tools to investigate the feasibility of some of the solutions you would consider. Okay? Now, the first primary thing we're trying to work with is, well, look, this area that we're looking at, what are we actually working with here? Okay? Now, it's interesting because I think some of you guys have noticed that this is not as desertified, and that's actually probably the word, than it is now. How old is this photo? Does anyone know?
2006.
Yeah, so it's almost 10 years old now. No wonder that some of this actually still looks like grass, unlike what it looks like at the moment. So, we've got an area in here that we're interested in working out. Okay, for instance, if I put to do this, okay, there's an area in there. Okay, now just to make this highlight, I wonder if could you hit the lights for us, please? Just get all the lights. Perfect. Okay, so now you can see it fairly clearly. All right. Now, just before I talk about the area itself, I don't know how many of you have looked at this shape and noticed how unusual it is. In fact, the serpentine wall is the graph of a sine curve, which some of you know what that is, and some of you will discover that later this year. And not only is it a sine curve, but it's a curved round sine curve, which is a tangent to this parabola. Can you see it there in green? Yeah. Just highlighted there. Bam. Right there. It's a bit hard to make out. That's okay. That's all right. It's important that you guys can see it. Right? No, it's okay. It's all right. The important thing is you guys get it. That line there is a tangent that forms around here following the curve of the parabola, right? So architects are often very mathematical people, and they kind of sneak it into their designs a lot. All right, now, we're trying to work out, let me get rid of that parabola. Yes?
Were the architects like that smart that they designed the school in the shape of the school emblem?
Actually,
It's actually the shape of the school emblem.
I suspect it was in the opposite order. I think the school was designed first, and the emblem came after that. I suspect.
It's like the villains like the
That's exactly right. Yeah, you can see the C, can't you? Okay, and you've got the diamond going all the way around. Okay, now a primary problem that you guys are going to encounter is, well, suppose we wanted to cover this whole thing in new grass, right? Make it nice and green and alive, okay? Clearly it's going to cost a lot of money. But the question of whether this is going to be worth it or not is very much dependent on how much money, how long is it, all these kinds of questions, okay? So this shape here, and we might hit the lights again actually, maybe you can do it, this will be easier. This shape here is a bit of a mess, right? Tell me what kinds of shapes do we know how to calculate the areas of? Okay, rectangle. Someone give me another one. I heard a circle. I heard triangles. What else?
Pythagoras.
Okay, so if we have like a right angle triangle, we can do some length here. We are thinking of area here though. I think I heard a square. Square. Trapezium.
Hexagon.
There we go. Okay, alright. Hexagon, that's interesting that one got mentioned. Hexagons.
Your shape.
If I understand correctly, and you can tell me if I'm wrong on this one, I don't think we learn a formula for the area of a hexagon, do we? I don't think we do. Now there is a way to do it, isn't there? Right? We can divide up this shape into other shapes that we know how to calculate. Okay? So here we go. On your piece of paper, I just want you to jot this down first, and then I want you to go and have a think about this later. Here's our first approach for this, and the hexagon has taught us what direction to go in. Method number 1. To take this weirdo looking thing, right? Like the hexagon, we can consider it as, method number 1, a composite shape. Or a composite figure. Okay? So we remember this, right? We've seen very simple ones before, and like you pointed out, there's one on the board. That hexagon over there, how can I divide it up? How shall I divide it up? Okay, so 6 triangles would work, wouldn't it? Or is it 6? Let's do it. Let's see. I got one up there.
Oh wait, I mean like from a point in the center, you like...
Okay, so I could put a point in the middle and then go outwards. Okay, or I could just do this. That would achieve the same result. It's still all triangles. Okay.
So what's the title of what this thing is?
Okay, now here's the thing, right? This is great. This is perfect. This perfectly embodies what we're doing, right? This hexagon, how many ways could you divide it up into triangles?
3.
Loads. There are loads of ways, right? Yeah. I could put the lines anywhere. I could put points. I could construct.
6, 7, 8, 9.
The whole point is there are many varying and valid ways to solve this problem, okay? But they all come back to this idea, that it's a figure made up of multiple shapes. Have a look at this guy. This here, method 1, composite shape. Composite figure. This here is an irregular shape, right? But we can divide it up. We can consider it as the combination of several other shapes, okay? Now, there's a really good reason why you might consider that. For instance, I have some straight lines over here, right? So I could divide up a triangle over here, or maybe even a rectangle of sorts, okay? But then you've also got these arcs around here. What shape should I use to get close to those? I would use circles, wouldn't I? Or semicircles, or quadrants, or whatever was relevant. So method 1, the composite figure, is about approximating our area. That's okay. I forgive you. I'm merciful and gracious like that. Approximating our area with a whole bunch of other shapes, that we have formulas for. Now, just as an aside, this is a classically mathematical thing to do. And in fact, all the way through your mathematical career, so much of what you do in maths is designed to do exactly this. Take a problem that you don't know how to solve. Look at this mess. Okay? Can we transform it into a problem that we do know how to solve? All of these nice, perfect geometric figures which don't exist in real life, but they're pretty close to what we actually want. Now, I'm not finished yet, but I've just illustrated a bit of a start, and you guys will need to finish this, right? You can see I've got a big rectangle-ish shape, right? I say rectangle-ish because it's not exactly a rectangle. If you pay very, very close attention, these angles here are not all right angles. It's slightly off. Okay?
There's more out in the middle.
I've got another rectangle here, a couple of triangles here. Now, I've got these curved shapes in blue. The reason why is, if you look at the actual shape there, these blue shapes are not part of the area I'm interested in, right? So for me, this is my code to kind of Don't add these, you should subtract these. Okay? Now here's the great thing about this, right? This is a real life problem. This is applied measurement. Okay? There's no back of book. People were asking me questions like, how many shapes should I use? People were asking me questions like, this part up here, right? You'll notice a little bit of a curve. Can I not just make it a triangle? Which is a fantastic question, because guess what? Maybe we can. All I want is an actual number out the other end. 100 square meters, 200, 300. I'm not even sure what ballpark I'm in. And part of the reason why is because this whole time we're kind of missing some crucial information. Any suggestions? What would I actually need? Suppose you have got some. I'm going to need some measurements, right? So if you have a look on your image, you can do that now. If you have a look on your image, right nestled in the bottom right hand corner, okay, there is a little bar, and it says, it should say 10 meters. Okay. Do you see it there? 10 meters? So now you can actually make some measurements, pixel for pixel, to work out what the size of this thing is. Right? You're going to need to do some conversions. You're going to need to calculate this fairly carefully, but it can be done.